This video is about how to use the Modern ATTiny Microcontrollers in your custom circuits with Arduino. The Modern ATTinys are the same AVR 8-bit architecture as the classical ATTinys such as the ATTiny85 and other microcontrollers such as the ATmega328. But they are a lot more recent and you can really notice the improvements. They are superior to all the classical ATTinys, and in their 32 kilobyte 20-pin versions they manage to be better than the ATmega328P whilst costing less than half as much. However, if you used to testing your circuits on a breadboard and programming with ISP programming, you will have to overcome a few hurdles. These microcontrollers only come in SMD mounts, so you have to put them on adapter boards in order to use them with a breadboard, and we will show you how to do that. Similarly, they are programmed with UPDI, not ISP, so you will need a programmer for that, and we will show you how to make one, which is actually quite simple. They do have one downside, mainly offset by upsides, so we will talk about that also. As always, if you like this kind of content and want more, don't forget to like and subscribe. So, what are the Modern ATTinys, and more importantly, what's the point for us in using them? Okay, Modern ATTinys are 3 series of ATTiny microcontrollers which have come out since 2019, right? They're called the Tiny AVR 0 series, the Tiny AVR 1 series, and the Tiny AVR 2 series, right? And, for reference, the classical, now called classical ATTinys, came out in early 2000, and that's around when also things like the ATmega328 came out, right? So, what do we gain from using these things rather than the other ones? Well, for starters, they're all cheaper. These things are cheaper, and they're cheaper than the ATTinys, but they're also cheaper than something like an ATmega328P, right? You can actually get in the 1 series and the 2 series, there are 20-pin parts which are pretty much, and they have 32 kilobytes flash, and they're pretty much as capable as an ATmega328P, in fact better, because the internals are better, right? But they do have fewer pins available, but not by as much as it might sound, not quite those 8, more like 4. But yeah, they're suitable replacements, and they're about 40% cheaper. So yeah, they can even be used to replace not just those classical ATTinys, and that easily enough, but even things like the ATmega328P can be replaced by some parts within this series. And it's quite a direct replacement, so same amount of memory, right? And the other one is, well, the series are quite complete. So within each series, there's many parts, and they all have the same peripherals. They're the same internal. They have the same things available, right? However, there's like different packages. There's for the 0 series, for example. Let's grab the 0 series. There's an 8-pin package, then there's a 14-pin package, then there's a 20-pin package. And then for each package, then there's also memory options, right? And whilst the 0 series only goes up to 16 kilobytes flash, the 1 and the 2 series go up to 32 kilobytes flash, and all the other series also have those 8-pin package and the 10-pin package and the 14-pin package, and all of these also have a 24-pin package, but that stuff is not really hobbyist friendly. It's actually meant for PCBs assembled with pick and place machines and soldering reflow. It's a completely different kind of packaging. But the other ones are stuff that you can use as a hobbyist, and it's quite straightforward, and we'll show you that. So, if you figure out you need more pins, you can easily find one with more pins. If you're on the 14 pins and you find out, oh, I have more peripherals, more lines, I need more lines than I expect, you can promote to a 20-pin package, and guess what? The program is still the same, because the series is still the same and nothing changed. And you can actually, sometimes you can actually go from one series to another series and the program is also still the same, right? A few things have a few details, and there are a few possibilities, capabilities which are specific to a series, but generally, especially if you're promoting, if you get into a newer series from a 0 to a 1 or 1 to a 2, you can often just go from one to the other one and the code is the same, right? And you can also easily, within the series, you can also easily go up in memory. So you find out you need more memory, part with more memory, and you're at the 14-pin part, and you find out that your 8 kilobytes flash are not enough. And yeah, you can find a 16 kilobytes part with also 14-pin package. So not all combinations of package and memory are available, but mainly they are, right? And the one major advantage also overlapping all this is that in the Arduino world, we use just this one megaTinyCore for all of them. And this is like quite a lot of possibilities in there. And if you've learned how to use that, to program them, to do the thing, if you learn that for one of those parts, you've learned it for all of them, right? Because they're all the same. There might be a few additional capabilities in some series that there aren't in the other series, but within the same series, your program doesn't change, doesn't really need to change. But even across series, you've learned one, the way you've programmed them is the same for all of them, right? The core is the same, you learn one and now you have 30-something possibilities in there. 100 and something if you consider other variants like the temperature range supported and things like that. But in terms of like just the combinations of pin packages with pin counts and memory sizes, you have, around 30, 40 combinations in there. Learn one, you get 40 bytes. You can do any of those 40 bytes, right? So this is especially important now that we still have the situation of semiconductor shortage. Because guess what? You're there, you're trying to find something right for your project. You don't find it, but you can easily find a part which is equivalent, right? Or good enough. Or you can just go slightly better, a little bit more memory or a few more pins. You don't really need the 20-pin part, but it's the one available and it's fine because it's going to be the same software, right? Or you can even transit to another series, especially if it's an upgrade, right? You're doing a 0 series and you're not actually finding that part. Move to the 1 series. If you find it in the 1 series, and that's going to work. And in fact, the 0 series is the simplest of them all. So it's the special features are present in the 1 series and the 2 series, not the 0 series. So then the actual features are better. The main one, I would say, is that the internal oscillator is vastly superior to the older stuff, the classical stuff. Classical stuff, it was 8 megahertz and you can divide it by 8 optionally, right? So you get it 8, you can run it with 8 megahertz or you can make it give you 1 megahertz. That's it, right? There's a few parts that had one or two more dividers, some trickeries, but other parts didn't have, but that's about it. This one, they will run at 16 or 20. So the same oscillator has a 20 megahertz mode or a 16 megahertz mode, and then there's a lot of dividers in there, so you can actually make it run the part from the internal oscillator at 20, but you can make it run at 5, or you can make it run at 12, or you can make it run at 4, or you can make it run at 1, or you can make it run at 2. You have tons of possibilities, and those things they become very useful if you're trying to play with situations like your voltage supply can only provide you a certain amount of voltage, like with batteries, and you want to get the fastest possible clock that will work with that voltage, but you don't want to have to add an external crystal or whatever. And with these superior internal oscillators, you can find it, right? And a biggie one also in this internal oscillator is that the precision is a lot higher, right? The classical part is the error on the frequency of the internal oscillator is plus minus 10%. And that means that for serial speeds above about 9600 baud, anything more than that, you're in trouble, right? It's likely not going to work reliably. Maybe you're lucky, maybe you're not. These modern ones, the error is, well, the baseline error is plus minus 4%, right? However, they record, at the factory, they record the error versus the 3 volts, in 3 volts and 5 volts, the error versus what it should actually be. And that information can then be used by the implementation of serial to reduce even further the error range. So, and definitely the megaTinyCore does it. So that means that in practice, for things like serial, the error is actually plus minus 2%, not 4%, but plus minus 2%, thanks to that. The information available there and the core using it, right? And then there's a bunch of other things. Let's say the biggest one is the ADCs are superior. They're better than the classical in all 3 series, right? But on the 2 series, they're even better than that because they're not only faster, but it's actually 12-bit instead of 10-bit. And there's also extra facilities in there, like there's a programmable gain controller that lets you multiply the input of the ADC by a certain factor up to 16 times, and then the ADC reads it. So that lets you read much more precisely smaller voltages, for example, and it has a fast 8-bit mode, which is actually faster than the 12-bit, which is not something you would find in the older ones or even in the 1 and 2 series, where if you want fewer bits, it's fine, but it takes the same time. This one will actually run faster if you ask for just 8 bits instead of 12 bits. And similar, there's lots of other things in there which are built-in peripherals. So there's things like analog comparators, there's custom configurable logic in there, there's event systems. They even have built-in real-time calendars, right? Although the Zero series does not support the 32.768 kilohertz crystal, which is the one you would use to get timekeeping, and instead you would have to use the internal oscillator for the low-frequency internal oscillator, which is a different one, and that's not actually good. So I wouldn't consider that as really having a real-time calendar, but the 1 series and the 2 series do, right? But beware that these crystals are very sensitive, so it's not going to work on a breadboard. It's highly unlikely you can even get that thing to oscillate on a breadboard. But if you're designing a PCB, you have a built-in real-time calendar, proper one, inside your microcontroller. You don't need an external module for that. It's there already. Okay, what's the downside? Because it's always a trade-off, right? Something. What's the downside? Okay. Let's say there's 2 things which are hurdles you need to overcome in order to use this with the same ease as you would use, say, an AT-328P, right? So there are 2 hurdles that need to be overcome. And then there is something which I consider a downside of these parts. A real genuine downside of these parts versus the classical ones, right? First, the hurdles. Programming. It's not ISP programming anymore, right? So Arduino is ISP programmer, as you've seen in our previous videos with the AT-328P. To program that, you would use an Arduino as ISP programmer. No, that won't work here. You need a new programmer for this. You need a UPDI programmer. Fortunately, you can make one. It's called a serial UPDI programmer, and it's made with 3 parts: a USB to serial adapter, a resistor, and a Schottky diode. And it is very simple. We'll show you how to do it. It is so simple you can actually make a programmer on a breadboard, which is quite ridiculous. On the very same breadboard where you have the part you're testing, you can actually improvise a programmer in there, just putting those 2 parts and wiring a USB to serial adapter to it. So yeah, it's that straightforward. And once you overcome that hurdle, that tiny bump, then you actually get a better programming system. So UPDI only needs 1 line for data, right? There's power, ground, and a UPDI line. That's it. ISP programming used 4 data lines, plus the power and the ground, so 6 in total, right? This thing uses just that 1 data line. So that's a lot easier to wire. In fact, it's absolutely normal to memorize where the UPDI pin is, and when you're wiring things, you just connect it to there. You don't need to pull out the diagram, pin-out diagram, and go search each line and where, oh, this goes here and that goes there, and some line comes off and whatever. No, that's just that 1 line. right? Even better, UPDI has its own clock. So what does this mean for us? Well, classical parts. If you configure the clock on the core, you've configured the clock on the programming. So a practical example, you have an 80 megaTinyCore on the breadboard and you want to run it from the internal oscillator, but you make a mistake and you burn fuses to make the thing use a crystal. And you don't have a crystal. Now you cannot do anything with that part. You cannot actually reprogram it, burn the fuses back to being internal. No, it won't work. That part now will only work once you get the crystal and the two load capacitors and wire it to that part. And then when it has that external hardware you told it needs to run the core, then it can be programmed also. So it's not just the core that won't run. Nothing at all will run, right? With UPDI programming, no, it doesn't care. Whatever you do on the core clocks, whatever, it doesn't care because UPDI is separate. And it has not just the one clock, but it has 3 clock speeds. And also linked to the speed grades, which is the same kind of thing as speed grades as you have on the old parts. These new parts also have speed grades. So if you can supply a higher voltage to it, it can actually run UPDI faster and can program faster. Although even the baseline one, the simplest one that runs 4 MHz, that runs for the lowest voltages, can already program that thing at about 220,000 baud, right? So yeah, and then the next one is twice as much, and then the other one is again twice as much. And in fact, the fastest one, you start bouncing against the limitations of your USB to serial adapter, or even your Windows driver in your PC. So at that point, it's not at all the microcontroller that's actually limiting the speed at which you can actually program the thing. So UPDI is actually much better. And by the way, if this serial UPDI programmer and the knowledge of how to program with UPDI, this thing then works with actually all the other modern AVR parts, such as the DA and the DB and the DD series, right? So you can quite easily just buy one of those, and now you have the hardware to program them, and you just start trying stuff out with them, and it's fine, right? So yeah, it's a small hurdle, and then it actually gives you a lot of benefits. A somewhat bigger hurdle is that none of these parts, in all the 3 series, none of them have a DIP package, right? It's not like the 80 megaTinyCore, where you have the pins that go down and it fits exactly on the breadboard. They don't. They all have only SMD packages. Now, they do have one SMD package, which is crazy, and you really can't do it. You can't manually solder that stuff or whatever. That's really meant for stuff being machine assembled. And it's also tiny, really, really tiny. But the other ones are hobbyist friendly. For SMD parts, they're really my first SMD parts. If you're trying to learn to solder SMD parts, you would start with something like that, because they're quite big, there's quite good separation between pins, it's big enough that you can solder those things with an absolutely normal soldering iron, right? A cheap one even, you don't need any special tip, a normal sized conical tip, the standard, most standard one you can get, it will work for that, right? So that's the thing, but they don't fit on the breadboard. So what do you do? Well, we'll show you here what do you do, but basically you solder them onto an adapter board and you put some pin rows on the sides of the adapter board, turn down, and there you go. You've adapted it to a DIP package. It's a bit wider than a DIP package, but that stuff now can go straightforward, no problem, into a breadboard, and you can start testing it out. And it's actually how I started. I got introduced to this series was like that, get things, solder it into adapter board, put pin headers there, put it on the breadboard, and then start trying stuff out with it. And it turns out that actually, it's actually pretty straightforward. But there's this one hurdle here, which is you do need to solder an SMD part for the first time if you haven't done it before. And if you've not done any soldering, then this is a good reason to start doing it. But it's actually quite straightforward. As SMD parts go, this is really entry-level type stuff, and it's not a big hurdle to do this, right? Now, Finally, it's the actual, real, genuine downside, in my opinion. None of these parts support a crystal. That's it. They won't work with a crystal. A crystal, remember, a crystal is not an oscillator. A crystal plus two load capacitors together with circuitry inside the microcontroller, all that together is what forms an oscillator. And you know what? The circuitry inside the microcontroller doesn't exist in any of these parts for the crystal. It exists only in the 1 series and 2 series for the clock crystal, for timekeeping crystal, the 32.768 kilohertz one, which you could use to clock that part, only it would really go really fast. It would be executing a little bit over 32,000, almost 33,000 operations per second. Now, for comparison, the default speed on an 80 MegaTinyCore out of the factory with the internal oscillator, which is 1 MHz, is 1 million operations per second. And that thing will run all the way up to 16. And these parts actually run all the way up to 20. So these parts could run 20 million operations per second. So yeah, if you're making them run with the really slow crystal and it's only executing at about 33, slightly less than 30,000 operations per second, yeah, it is, I wouldn't call it running, I would call it limping, but yeah, it's doing something, it's just very slow, so it's not really useful. So I wouldn't count those in as that. And besides, as I said before, those things won't work on the breadboard, so you need a PCB. So, you know, normal crystal, put it there, 16 MHz crystal, whatever, no, these parts don't support it. And that's the real genuine downside. They do support being run from an external clock, which is a full-blown clock signal. So it's an independent, whatever, sub-circuit, whatever. Now, there's actually one single part that looks like a big crystal, and it's more expensive than a crystal, and that thing is the clock generator, right? But it is a self-contained circuit that generates the clock. It's not like the crystal that together with circuitry inside the microcontroller. No. This thing is like, does its own thing, and out comes the clock, and you can feed the clock to one of these parts, and then you get the precision of a crystal. You get the 50 part per million error instead of those 4% or 2%. No, here you get 0.0005% or something like that, right? It can be overcome, so you can run the crystal, it can be overcome. However, it does mean that, for example, comparing with an 80 MegaTinyCore, even if you do need a situation where you do need the precision of a crystal, with an 80 MegaTinyCore, even though it's more expensive than an equivalent part from the 1 series or the 2 series, because it can just run with the normal crystal and the 2 load capacitors rather than requiring a clock generator, which is a more expensive part. Overall, it's actually cheaper. So that means that in this specific kind of situation, the older parts can be superior, right? The older parts with similar number of pins and similar amounts of memory can be superior because of this, for this kind of thing, right? So that's actually the only downside. All the rest are benefits. You get a much more modern part. You get quite a selection of choices. It's quite consistent across. You know how to do one, you know how to do all the 40 other parts within the 3 series. And it's well worth it. And nowadays I basically, for the kind of use where I'm doing AVR 8-bit stuff, I use these things. And also, funnily enough, because the SMD parts are quite friendly, I often favor them over things like STM32 microchips, because I can manually solder these things easily. And it's much faster to do, right? If you're doing things with, pick and place machines and whatever, then, all the options are open. But if you're actually doing it yourself on a PCB, these actually are quite a very good balance. And they're cheaper. It's amazing, right? So if you're still interested, watch the rest of the video. In the rest of this video, we'll show you everything you need to know in order to use these parts to their fullness, and even how to use them in a very similar way as you'd use an 80 MegaTinyCore. So, before we actually go into how do we adapt a modern ATTiny to work on the breadboard, we need to first figure out how do we find them, right? So here's from a well-known electronics supplier, here are some ATTiny. Just literally search for all things they have to say ATTiny, right? Now, looking at this, which ones are the modern? Now, I know that there's like 1, 2, 3 modern ATTinys here, right? But yeah, how do I know this? Well, that's what I'm going to explain. Also, this is from a datasheet. This datasheet is only for the 8 kilobytes and the 16 kilobytes parts and only for the 0 series, right? This is the list of options you have, right? There's all this code. So what do they mean? Why do we care? It kind of says it here, but there are ways of quickly sort of figuring it out. So you can mentally produce the code of what you want. That's the point. So how? Right here, datasheet still product identification system. This explains how the codes are assembled, right? And with this, you can actually spot the actual modern ATTinys from the rest, and you can actually figure out the code for a modern ATTiny you might want, right? So, ATTiny, yeah, okay. Yeah, I wouldn't expect otherwise. The flash size of the memory flash size in kilobytes. So here you see 16, but it can be just a 1 digit, so 8, 4, 2 even, right? This is the series code, 0, 1, or 2. That's literally that. I have here a datasheet for the 32 kilobyte parts of the 2 series, and you can see here there's a 2, as expected, right? The last digit is a code for the number of pins of the package, not the number of pins, the code. And you can see here the translation from the codes to the actual number of pins. There is, in addition to that, and it's not covered in this datasheet, hence that's why it's not here, there's also an 8-pin package and has code 2. So code 2 is 8-pin package, right? Now, with this, you can go back to here and you can start spotting those things. So ATTiny 8 kilobytes, series 1, 4, that's the 14-pin version. Here's a 2 kilobyte series 0, and this is one of those 8-pin parts, right? This one, no, this one is not, and it doesn't match at all. And here, oh, yeah, once again, 4 kilobytes, series 0, and it's an 8-pin part. This one, no, this one is not a modern ATTiny, neither is this one. The codes simply don't match the pattern. So yeah, at this point you kind of have that pattern already, and you can even form it from the other way around. You know how many kilobytes you know which series you would like, and you have an idea of how many pins you need for your project, so you go for a certain pin count. And with that, you can already in your mind produce a code that you can then search for, right? So, here, in terms of choice, well, memory is based on the size of your program, so yeah, you have figured it out yourself. Remember that 0 series only has up to 16K. The actual series is to do with the features. Why do I choose one series versus the other one? Okay, let's start by this. 0 series is usually cheaper. So if you don't need features that are only present in the other ones, it's probably the best choice, right? But what features do you might need from the other ones? Well, a DAC means series 1. That's the only one that has a DAC, so series 1, right? You want to use the advanced ADC, which has 12 bits. That's a series 2. You have to have a series 2, the other ones don't have that. You want to use RTC, and remember, because of the kind of crystal it uses, it's kind of a PCB application, because those crystals are quite sensitive to electric parasitical capacitances in circuits. Okay, that's RTC, built-in RTC, series 1 or 2. Series 0 wouldn't work. You need 32 kilobytes. You can't get away with just 16. Okay, that's only series 1 and 2. Again, series 0 doesn't have. So that's sort of how you figure out which series do you want, right? And yeah, usually series 0 is for the same everything else. Series 0 is the cheapest one, and it goes up, and series 2 is often the most expensive. Series 2 is also the most modern. I mean, it's very modern, while series 0 started coming out in 2018. Now, pin count, yeah, it's your project, right? You know if you need, like, you're running a wire, so I2C, you're running SPI in parallel, and you're running also serial on that thing, and those things they already demand from you 2, 4, and another 3, 7 pins. So just 7 pins for that. So yeah, okay, depending on the other pin counts. Well, for starters, the 8-pin one is not going to work because remember it has to have power pin. So it's not going to be enough. So you need at least 14 pins. Now, depending on the other uses, maybe you need some more. So that's how you go about that side. Right. Very important. here in the second part, the beginning is the most important one. This is the package type. What's a package type? Well, let's go here. You can see here package drawings. This is for the package type. An SOIC is this, right? A VQFN is this, right? This is the first, number one. What we've seen so far is the SOIC 300, which is called here SOIC 300, but it's actually called here something else. And in fact, you'll need to see it with a pin count to see which one is which. Because the naming convention is actually, there's no actual proper standard for this. And you can even see QFN here and see VQFN there. So it's not even consistent within the same document, right? So what you do know is that for the 14 pin, there is an SOIC narrow, and we'll see in a second why is, well, how can you confirm it's narrow, if you will, not just from the drawings. And there's an SOIC wide. Those are the ones you've seen so far in this video, right? Those are the ones we use here, and they are the ones with nice, spacious things. And how do I know besides actually having had them? How would I know it beforehand? Okay, look at the dimensions. And I'll call your attention to 3 dimensions. Maybe the most important one is this one. This is called the pitch. It's the lowercase e here, and it's used throughout this document, lowercase. Another document from the same manufacturer, lowercase E is pitch. Pitch is the distance between 2 pins, or in the case of the VQFN part, it's between 2 paths, since the VQFN doesn't have any pins, right? And also the E, uppercase E, this is the width, and you can see here from one extreme to the other, and the D, which is the length. Now, to actually know how big this actually is before you have it in your hands, you can't just look at this drawing. You need to check the measurements, right? Now, look here, and you can see that the pitch, the distance between pins, is 1.27 millimeters. Because millimeters is here, the unit for all of this, 1.27. You can see here the width, and this, for example, is 6 millimeters. And now I'll show you the wide one, right? So they call them wide up here, and the width is 10, not 6, 10.3 millimeters. So this is why they call them this one wide, and because it's wider. So okay, this is the one you've seen. It's 1.27. So what's the use for this? Well, let's look at this VQFN. This is the 20-pin VQFN, and you look at this and it's okay, and you think, yeah, you know, it doesn't have pins, but it has these things on the side. I should be able to solder it. It looks okay, right? And same here. Well, same dimensions. E, distance between, in this case, paths. It's 0.4 millimeters. It's not even half a millimeter, right? The distance between this thing, which looks quite, it's 0.4 millimeters, right? Soldering this, it's by hand with soldering iron. It's not really feasible. I mean, some people claim to have managed it. I think for bigger ones, actually, but And you can also see in the other ones, you can see here again the D and the E, and this being square, they're the same, right? And you can see they're 3 millimeters. So this seemingly nice big thing is that this is 3 millimeters, right? It's like 3 fingernails thick, basically, roughly. It's minuscule, right? Now the 24-pin one is a little bit bigger, but it's the distance, the pitch is even bigger, but it's still only 4 millimeters across. So yeah, these parts are tiny. They're not really meant for people soldering them with soldering irons. They're done with typically pick and place machines, certainly solder paste, stencils, ovens, right? Maybe it's possible to do with a hot air gun, maybe, but it's not going to be doable with a soldering iron. So that's my point. And this brings us back to here in the product identification system, where that first letter is the package. And my point being, don't go for the M, right? That's it. And this one is actually the naming convention. This is, sad. But anyways, just choose the one that has the count of pins that you want, because you can see it from here, and then just go for it if it says S or SS. It has an S in there, possibly followed by another S. That's what you want. You do need to make sure if it's the wide or the narrow, if you're actually designing your own PCB, obviously. And one last detail on that one is that this one for the 2 series, there is an additional package type, which they're saying it's called VX, meaning it's a TSSOP package or an SSOP package. And the process of figuring out what it means is the same. Go back here, package drawings, and you can see there's a 14 pin is the one that's called TSSOP, the 20 pin is the SSOP. Now, if you go see the drawing, it looks a lot like those SOIC, whatever, that we've seen so far, except, look at the pitch. It's 0.65 millimeters. Notice that this BSC is just a note down here saying it's actually because it's the value, theoretical value, because, you know, real world, there's tolerance is not going to be precisely that. That's what this means. The actual unit is up here, millimeters. So 0.65 millimeters, right? So look at this picture. We've shown you this before. You can see at the bottom is an SOIC wide. It's 20 pins. You have 1.25 millimeters separation between pins. That's the pitch of that, is 1.25. Above it is the SOIC narrow, which, as you can see, is narrower, and it has the same separation, same pitch separation between pins of 1.27. Above it, it is actually not an ATTiny part. It is an STM32, but it's also an SSOP, right? And it has also 20 pins, and that part actually has the same pitch as the ATTiny, modern ATTiny part with this kind of X code in there would have, 0.65. Notice the distance between the pins, right? Compare it with below. This is why this part is a lot harder to solder. It can be soldered by hand with a soldering iron. Indeed, you can. All right? It's just going to be very hard, and certainly I wouldn't go for that thing as, you know, my very first SMD soldering attempt, because, yeah, that's not at all friendly if you don't know techniques, and even if you do know, you're likely to make mistakes and have to correct them, so you do need to know how to correct them. It uses copper wick to pull the excess solder out. That's basically it. But yeah, so my recommendation on this thing, and remember this only applies for the 2 series, is don't go for the X either. Don't go for the M. Absolutely not. If you're the one that has to actually assemble the thing with a soldering iron, if you're paying somebody to make you a PCB pre-assembled with the things in there, and that's done with a pick and place machine and all the proper ways, yeah, sure, go get the VQFN part, because if you need the small thing, because, yeah, and if you don't need to maintain it or solder it or whatever, then yeah, go for it. Otherwise, frankly, I don't see the point of using this TSSOP and SSOP parts here, because there are the other ones there, right? If the problem was one of size, but yet I also need to solder it by hand, okay, it's understandable, but that's like a very narrow use case for this thing. So yeah, I would recommend go for the S and the SS, depending on what's available with the pin count you want. And if you noticed if you go exploring the package things, you'll find out that one of them is for one pin count and the other one is for the other pin count, right? Right. This is enough, right? At this point, this is enough to actually select a part that's good for you, right? The other things are sort of additional features, if you will. The first letter is the temperature range that the manufacturer guarantees that this part with this code can work properly within this temperature range. So you can see there's a narrower one and a wider one. Typically the narrow one is cheaper, right? Sometimes due to the way electronic suppliers sites make their pricing on the basis of stock availability, sometimes you actually find that the wider range is the cheapest one. Just go for the cheapest one, unless you have situations where you do need the extra thing. Say you're doing a device that's going to be under the direct sunlight for long periods, right? And there's not really any proper airflow in there. Yeah, it makes sense then. Or it's something that's near something hot, really properly hot, right? And again, no proper airflow. Okay, in those cases, it might make sense to actually go for the part that is guaranteed to work at higher temperature. Remember, guaranteed doesn't mean that the part that's not guaranteed won't work. It does mean that the part that's guaranteed will for certain work. That's what it means. But that doesn't mean that you cannot get a not as good part and be lucky and it actually does work, right? Now, one detail on this, in the 0 series, not in the 2 series, in the 0 series, you can see here that if you look at one of these, and let's look at here, 8K, 0 series, 20 pins, right? And you can see already SN, so the S, remember the S things, right? SN and SRF. And you can see here the SF as it matches what's in the product identification system. The F is the wider temperature range, right? Now, notice that there's something called max CPU speed and supply voltage. Notice they are, in fact, different here in this table, right? So you might think, okay, the SF, so the wider temperature range, as you see here, wider, part is inferior because, we can't run at 20 megahertz, right? And it also needs a higher voltage. No, that's not how you should read this. You should read this as within the normal temperature range, they're both the same. Within the extended temperature range, so in this case it's after the 105, between 105 and 125, then it operates this part. The other part is not guaranteed. The SN is not guaranteed to operate, period, right? So don't expect it to work. At 115 degrees centigrade, don't expect it to work, right? Maybe you're lucky, don't count on it, right? The SF is guaranteed to work, but it has additional conditions, right? The maximum speed is only 60 megahertz, not 20. The minimum voltage is up. It's from 2.7 volts up. It's not 1.8. That's for the extended segment. So that's how this should be read. It shouldn't be read as this part is actually inferior in all ways except the temperature range. But rather, for the full temperature range, so that includes the part above 105 up to 125. It works, but you need limitations. This actually in practice means that it actually works fine for the normal temperature range, but it does require some limitations. That's not a problem here. If you look at the same page, ordering information, you can see that it doesn't really matter. But for this one, it doesn't matter if it's the full temperature, extended temperature range, or the normal one. It doesn't matter, right? Now, last bit I want to cover is the last letter and this VAO, which only exists, by the way, on that datasheet. So it's for the 2 series, 32K. It might be there for other datasheets or for other series and other things, but for these 2 that I have here and what they cover, only this one has the VAO. The 8Ks and the 16Ks on the 0 series do not, right? So, last letter first. This thing, VR, is only important for people with things like pick-and-place machines, right? This is how multiple of these microcontroller chips come packaged. Are they in a long tape and they're all there inside the tape, or are they not in a tube or in a tray, right? For a retail customer buying 10 parts, this doesn't really matter, right? If you buy something which is so, you might get a little piece of tape. Say you buy 10 units. They'll count 10 and they'll cut it and they'll give you a little piece of tape with the 10 units inside, right? If not, they're going to be loose within the electrostatic bag or maybe in a little box, but that's about it. They're going to be coming loose in some way, inside the bag and so forth, but inside of it loose. And the other one's probably going to come in a tape. Now, if you're a big customer, if you're buying 1,000, and, well, if you have a pick-and-place machine, you want a tape. And you get like a tape, like a proper wheel of these things, and with 1,000 things. And you grab that thing, you put it in your pick-and-place machine, put it all in place, and then the machine will automatically be able to handle it from there. Pick it from the tape and place it on the PCB. That's why they're called pick-and-place machines, right? If it's not on the tape, then it can't. That's where it does matter. And I think older pick-and-place machines used at some point trays, but now it's tapes. Right? So for you, my recommendation here is get the cheapest one. Really, if you're looking at 2 options, they're exactly the same all the way down to here, and one has an R and the other one doesn't have an R. Choose the cheapest, right? Unless you have a pick-and-place machine, in which case, and you're ordering 1,000, in which case you want a tape, so you want one with the R. That's it, right? Last bit. The VAO, which might be there or not, if it's there, it means that this specific chip with this code has been certified against standards for automotive manufacturing. That's cars, that's motorcycles, that's trucks. This is a chip which will resist the kinds of mechanical strains, we're taking vibrations, various speeds, various amplitudes of vibrations, possibly also things like electromagnetic interference. Think internal combustion engine with spark plugs firing, and firing a spark from a spark plug in the electromagnetic spectrum is like a shout. It's a wide frequency range emission of energy, really. So these things are certified according to the industry standards that indeed can work within those conditions as covered by those standards. That's what it means. What does it mean for us? Well, it means they cost more money, right? That's the only thing pretty much that's going to mean for us, right? You're highly unlikely to, unlike the temperature range, you're highly unlikely, for one thing, you're highly unlikely to find these things outside special order in a normal retail electronic supply. That's the one thing. And the next thing is, even if you do find them, you're highly unlikely to find them cheaper, right? Because these things are basically the same as the other ones, only this one have been checked and tested that they do work in more extreme conditions than the other ones. The other ones might not. This one does certify that they do work. Yeah, it costs money to certify them, and possibly even the manufacturing is different. It costs money, hence they're going to charge you more money for it. Hence, there's no point in getting a VAO unless you're designing products for automobiles, right? And it's actually the kind of location in an automobile where it does need to be certified for this, rather than in the nice bits, probably in the nasty bits, right? That's what it means, right? So, with all of this, it's now much easier to sort of come here and sort of figure it out, right? You want, I don't know, let's say I want a 16 kilobytes 2 series because I need the nice ADC, and I'm making like this crazy circuit, so I need 20 pins. I don't want the M because it's going to be not something I can do. I'm going to solder it by hand. ATTiny 32K 2 series. It's the 6, which has a 20 pin dash, and it's one with an S. I don't know if it has 2 S's or 1 S. I don't care. It's not the S, right? And it's not the X. So there you go. This gives me immediately the parts I'm interested in. And then I'll just go down there and see, based on availability, there's only these two. And based on, in this case, you can see the only difference is this last letter, which is, well, there's no R here, so there's for these ones, and notice they're not even available, the ones in reels. And yeah, they're sold in entire reels, and it turns out it's 1,500, so there you go. So it's only between these two, so unless I have any special need, I'll really just pick the cheapest one, right? And that's the entirety of it. And as it so happens, it's, the U is the narrower temperature range, as it is indeed, in this case, it is indeed the cheaper one. So this is it. This is how you'd go about getting this. And now, with this, it's much more easy. Now, you can actually choose the part that you want to get, or test, or whatever, and then, well, let's go into the next part, which is how do we put this thing on a breadboard? How do we make it so that it can go onto a breadboard, and we can actually start doing stuff with it? To make this thing be usable with a breadboard, you want to put it on an adapter board, right? So what do you need for that? You need the actual microcontroller chip, you need the adapter board, the pitch, this is the most important detail, the pitch on that adapter board should be the same as the pitch on the microchip, meaning the distance between the pins on the microchip should be the same as on the adapter board. Remember from the previous chapter, it's 1.27. This is the SOIC, what a microchip calls an SOIC 300 packages, the SOIC wide, right? And it has 1.27. Notice the adapter board, it's even written in there. It's 1.27. It has another side. The opposite side is actually 0.65. So it comes with two versions. You want that thing. You don't want to see 10% off. 10% off means 10 pins later, it's going to be 100% off, right? It needs to be the exact same thing. That's very important. You need also pin headers, right? And rows of 10, they're already pre-cut, so I cut it from a 40. I buy them in rows of 40, and I just cut them and use them like that. They're going to be pointing downwards because that's what's going to be going onto the breadboard holes, right? For the actual soldering job, you need, of course, a soldering iron. It can be a normal soldering iron. It can even be a cheaper soldering iron. This thing is big enough, the chip package is big enough that it's actually no big deal. With the normal conical tip, really the normal one, the default one that comes in the $5 ones, fine, that works for this, it's fine. And you want some flux, liquid flux, not paste. SMD work is not the kind of situation where you put paste in there, you use liquid flux for that kind of thing. I have this bottle with the needle on the front that lets me dose the right quantity in the exact places where I'm going to be soldering stuff, not all over the place. And some people will use things like brushes from nail polish, that kind of size of brush to do the same thing. They'll brush it over there. I'll just put it there. You also need soldering wire. Notice, and this is optional but highly recommended, notice I have two sizes, right? First thing and important thing, get the kind of stuff that melts at around 220 degrees, not the kind of stuff that melts at around 270 degrees. The stuff that melts at a higher temperature is not really great for SMD work. I mean, you can do it, but it will give you more trouble, right? It's just not as nice. It's doable, not nice, and that's the cheap stuff generally. So try and get this stuff, which is not really more expensive. And if you go to an electronic supplier, they'll actually give you the specs rather than the random seller. They'll give you actually the characteristics of it, and you can see there the temperatures that, yeah, it's something that melts around those temperatures rather than something that melts at higher temperatures. The optional element here is thin wire. Thin wire, and this is 0.38 millimeters. Thin wire lets you dose much more precisely the amount of solder that goes onto the tip of your soldering iron. And here, this is important because in SMD work you use not that much solder per pin. It's very little, actually, surprisingly little, right? And if you have like bigger bubbles, bigger droplets of solder in there, you're highly likely to have a situation where you're trying to solder one pin and the droplet touches the pin next to it, and now you have a solder bridge. And now both pins are connected to each other, which is really not the point. So you don't want that, obviously. And it's actually also harder to correct. And you'll see in the video at some point, even though I'm using this thin wire, at some point I actually get a solder bridge, but there's so little solder in there that just by warming it up again and pulling it with the iron tip itself pulls enough solder that the bridge sort of disappears and things proper. And yeah, if you're doing it with a 1 millimeter, the normal size 1.2, I'm using a 1 millimeter here, that stuff tends to put bigger droplets there, and those droplets will almost certainly cause you problems that then you have to correct with copper wick, and it is a lot more frustrating than it needs to be, right? And as I said, you'll be surprised just how little solder you actually need there, right? Yeah, let's go ahead. Now, you can see the first part is really just putting the flux on the adapter body. You put the flux on the actual surface where you're going to solder your SMD component. Some people will also put it afterward. Once they've placed the component in place, they'll put some more. And yeah, be generous. That's basically it, right? Next is to place the component on top of the pads. Notice some work. I'm using less light than I'm used to here because of filming, and I'm also not using proper visual amplification to help me out. Yeah, it takes me a little while longer, but that's it. It should be fine for you. Make sure things are really properly aligned, right? And at this dimension, and the smaller the pitch, smaller the distance between pins, the harder it gets. If the pin is too close to the pad next to it, you're gonna get breaches, and those aren't quite as easy to solve, and it's a lot more complicated. Tie one corner, right? Just solder one corner, put the pin on a corner with the pad. Make sure it's properly soldered. Then do the same on the other side. You might need to sort of like push the chip a little bit if the rotation is ever so slightly off, so that the other side is also properly aligned, because it doesn't need to be off by that. There might be a few degrees rotation in there, and it means one side is fine and the other side is not. So that's the point. And you might need to go back and do it again. This is the point where you do that thing. Don't start going down the other pins. Just do it with those corners only, because you can always take it off. You can adjust here. Once you start doing the other pins, you can't do it anymore. You can't really rotate and adjust and move them and just say, no, this is all totally off, and desolder it and just take it off and just put it back on again. No. So once you're still working with those corner pins, it's still fine. After that, you've committed to it, right? Because the only way of taking something that's incorrectly aligned when you've soldered 5 or 6 pins is with a hot air gun. So if you don't have one, if you're talking the situation, as I said, with normal soldering iron, so do it then, and then you can start doing your pins. And notice this is done with like just a little bit of solder from the thin wire. So this is what I meant in practice, right? A little bit, it's enough for like 3 pins, maybe 2, 3, 4 pins. As I said, it's surprising how little it actually needs per pin. And just go and do one by one by one. And then the other side, one by one by one. You'll notice that in the end I'm going and doing a second pass. This is just to make sure that indeed the solder has melted properly, not just over the pin, but from the pin through and into the path, right? And that is actually properly connecting both of them. Again, I'm not using visual amplification, so this is a way of making sure that it is indeed good without actually being able to examine to the detail. If you really want to make absolutely sure, and this is even more important, it's with smaller pitches, with little tiny pins and things like that. I'll go with a multimeter and check conductivity, right? I check conductivity from the top of the pin next to the actual housing of the chip and against the pin header. Right, against the top of the pin header, or even the leg of the pin header should conduct, right? If it's properly soldered, it should conduct. And then I check against the pin next to it, and it should not conduct, right? And this is also to check where there are bridges. Here it's quite easy to spot them. Once the pitches are small, again, you need visual amplification to spot them. And this kind of thing just makes sure absolutely 100% that they're not there. And yeah, that would mean like checking one by one. So move the thing one, move the other one. Does it ring a bell or not? And you don't want it, and so forth. So I kind of have this process, and I'll go through the thing, and it will take me, I don't know, 3-4 minutes. But I will be absolutely sure that indeed it conducts where it should conduct, and it does not conduct where it should not conduct. But yeah, that's it. Right. After this, just pin headers, right? Notice I'm making a mistake here. But I want to point it out. What I'm doing here is the end, just doing one end, then adjusting the position of the pin header. So the way I'm grabbing it with the finger and push it against the board, and then desoldering that one end that's soldered, and then it actually adjusts it, so it makes it 90 degrees. It's one way of doing it 90 degrees, right? And the same thing for the other side, and only the ends first. Actually, this thing is best done, in this situation, it's best done with a breadboard. Right, and I didn't have a breadboard available. All of mine have circuits on it, which is funny enough. So normal. So you actually place them there, and then you put the adapter board with the microchip now soldered on top of it, and then you can just solder it to your heart's content. And you will know with absolute certainty it's going to be 90 degrees, and they're going to be in the exact precise position. Everything should be prim and proper. Also, when soldering further on, it's not going to move, and you're going to see. Well, in this video, it moves as you start doing the other pins. It's actually moving. So it should have been a breadboard for that. However, the technique of sort of hooking it with the finger and pushing it from the underside of the pin header against the board is useful when you're trying to do the other kind of things, which is you're using a piece of pin header, say 3 pins, as a connector. A UPDI programmer connector. You want to do it as a proper connector, and you put 3 pins in there, right? Turned up. In this case, you're not turning them up for a breadboard. Turned up. And you want them to be properly aligned. This is the best way of actually making them 90 degrees, right? And in this case, in such a situation, you can't actually put them on the breadboard. It's just 3 pins. It's not going to be, your board is going to be twisted. It's not 2 rows on each side. So it's not balanced. It's not going to be correct. This technique does allow you to force it to the right position, right? Hooking it with the finger in there and pushing it and melting the thing and then feeling it that it moves until it stops moving, and it stops moving, it's exactly at 90 degrees, and then you take it off. And that will give you like lovely, properly pointing up connectors, which otherwise it's quite unlikely. They'll be slightly twisted to one side or the other one. So that's really the essence. But yeah, if you're doing this, this phase, the easiest way is just get a breadboard, put the pin rows in there with the appropriate distance, put the adapter board in there on top of them, and then just solder them to your heart's content. It's really that straightforward. To program our modern ATTiny microcontrollers, we need a UPDI programmer. Now, luckily we can just make one. All it takes is a USB to serial adapter and some components. Now, in this case, the components are worked into a connector, so there's a resistor here, and there's a Schottky diode there, and that's it. And yeah, the way I've done this, you can see the lines are color-coded, so black is ground, and I've marked it here, so there's only one way this connector goes in correctly, and this is a serial UPDI programmer. Really, this is it. Right? Here's another example, which is even more ridiculous. A serial UPDI programmer conversion on a board. Same USB to serial adapter. This is just normal jumper wires, and the same 2 components are here on the breadboard. And this is not part of the programmer. This is the microcontroller being programmed. Right? So, yeah, serial lines, UPDI line. It's that simple. Now, if you look at the diagram, you can see that it's really as simple here as it was in the physical world. There's just those 2 components. It only affects the RX and the TX lines, and basically your RX is converted into a UPDI line by means of a Schottky diode that lets TX pull it down. What's the purpose of the resistor? Well, UPDI is just one line, and data has to go back and forth, which means that the programmer will activate it, but also the microcontroller will activate it. Now, the protocol is designed so that only one activates it at a time, so it's usually like request-response. But it might happen that those things get out of sync. So there is a small risk that the programmer and the microcontroller are both trying to move that line in opposite directions. Without the resistor here, you would have a short circuit which could damage either your USB to serial adapter or your microcontroller. With the resistor here, the current is limited, so that problem is solved. But, and yeah, there is a but. If you go to the megaTinyCore website, there is a page about making a serial UPDI programmer, and it is quite long and maybe a bit complicated, and there are good reasons for that. For one, it's actually talking about older ways, so the JTAG to UPDI, which we don't use anymore, and a previous way of making a serial UPDI programmer that only used a resistor and no Schottky diode. However, that's not actually the biggest part. The biggest part is, well, there are various USB to serial adapters. And I mean, I have 2 here, but there's actually an enormous collection of the things. And their difference is a lot more than just the connectors, which frankly for a serial to UPDI programmer, it's not that much of an issue. Well, not on the electronic side at least. The first problem starts with these 2 little things. They are actually the microchips that implement the USB to serial conversion. And there's many of those things, right? These 2 are the most common. This is one of the CH340 family, and this is one of the FTDI family, right? And as it so happens, these 2 are fine for using as USB to, for converting your USB serial adapter into a serial UPDI programmer, but this one, the FTDI one, might require you to change some configuration in the Windows driver so that it actually performs well, and this one doesn't, and it so happens this one is the cheapest one, which is funny enough. Other details are on the boards. there might or not be already in place a resistance between the TX pin on the chip and the actual connector. And if there is, then you don't need a resistor on the other side. And in fact, if there is and you put a resistor, it might actually be too much. So there's also that, right? As it so happens with this one, I know there's none. And this is quite a well-known form factor because this is sold. You can find it in the usual Chinese sellers and in Amazon and wherever, and they're extremely cheap, right? And these things are sold for something called an ESP01 module. And an ESP01 module is basically a module with the ESP8266 microcontroller, which you might know because it's compatible with Arduino. You can actually install Arduino programs into it, and your programs can then talk to other devices on the internet via Wi-Fi, because that's the special thing about that module, is that it actually supports Wi-Fi. And it's commonly used to make IoT applications in the Arduino world, because, well, it's so easy and it's also quite cheap. And that means that these things might have been produced in the hundreds of thousands or maybe millions, I don't know, but it's like they're all over. They're cheap and they're immediately recognizable because it's the black one with the yellow connector. Yeah, that's how people spot them. And yeah, this one I know for sure it works because I've used it. I just had a bunch of them, so I tried it. Also, as you saw, it's jumper friendly, right? It's absolutely normal, common jumpers. Yeah, they'll fit onto this connector. But as you can see here, this is a tremendous example of it. It will come out easily enough, right? Versus that dedicated connector. And you need to know where to put things, right? That diagram I showed you actually has the right pins, so yeah, that might help you if you need to. But yeah, the principle is this one. This thing is easy to use. Downside, it runs at 3.3 volt, so UPDI programming will not be any faster than about 220 kilobaud, which is still quite a lot of speed for microcontrollers that have at most 32 kilobytes of flash memory. So you're not going to notice the difference versus something that would run at 5 volts. One last detail is about, well, making a cable like this, or if you are doing something like removing the connector on one of these and installing your own wires, because you don't want to have to constantly go check which pins are what. The cable sort of solves that problem. You can see here it's color-coded black, and there's a black one marked there, so there's only one really right way of doing it thanks to that. Otherwise, you could sort of put it the wrong way around. But if you're doing it with jumpers, you then have to have a diagram or memorize the thing so that you know which one is which, right? So you might be tempted, and it's absolutely valid, to sort of take all of this off and solder your wires directly here, solder the parts either above or below so that it's transformed into a serial UPDI programmer forever and ever. And because this is so cheap, it's absolutely valid to hack it like that. There's zero concern in breaking something that's worth $1. So in that case, there is a little mechanical consideration. I'm going to show you it here on the side of the cable because it applies here. This little sleeve here is meant to protect the junction between the stranded wire and the hard metal, which is the solder. And this is because you're going to be moving these wires a lot, right? You're going to be plugging this in on the breadboard. You're going to be taking it out. You're going to be moving this stuff around, right? This moves the wires. If you don't protect in some way, most of the mechanical strength is going to go into the weak link. And the weak link is the point where the stranded wire goes into the solid metal. And it would apply the same if you have some wires going here and directly soldered into this. So here, there's the sleeve. The sleeve transforms all of these movements into something that's distributed across the whole thing, right? It becomes one unit. This side, for all effects and purposes, with relations to the movements on this side, is one unit. So that mechanical strain is not concentrated. Here is dispersed over the whole thing. And moving one of these things, it just wants to move the entire thing as one. So this is protecting that junction. Otherwise, this will break quite fast. And similar here, you would use something like, for example, thermal glue and just make a nice big blob around all the wires and around part of the board so that that mechanical strain then reaches that blob of plastic once it's solid and it disperses across and it doesn't get concentrated on, again, the weak links, which would be the places where the stranded wires go into the solder. That's it. And yeah, it's actually quite easy once you know the details. So now I'm going to show you how do you install this on the breadboard, wire it for operation, and actually wire it all the way to the programmer. And it's actually very easy. For starters, these chips only have 2 power pins. There's like if you look in the pinout diagram or in the data sheet, you'll see that basically it's the number 1 and number 20. So at the top, the left one and the right one. That's it. Number 1, so left side, is the positive and basically positive power, and the right side is the ground. That's it. Hence, we've already installed the decoupling capacitor in there because, well, you always need a decoupling capacitor. There's no reason to keep it out in this kind of thing. This is an adapter, almost like a mini Arduino board that doesn't do much Arduino-y stuff, but okay. And it's such a stupendously simple and easy place to put one of these capacitors that you might as well just put it there. And you can see, yeah, it's no big deal. So installing it is equivalently simple. Again, yeah, you know, the top side, the top left side is the positive, so you wire that thing to the rails. And of course, I've pre-selected the correct length of wire, obviously. And the top right side is ground, so you wire it to the ground rail. And that's it. This is sufficient for operation. I mean, you wouldn't do anything because it's not wired to sensors or actuators or LEDs or whatever. But yeah, this is enough, right? It's even simpler than with the AT-megaTinyCore. Wiring it to the programmer is actually very simple also. So the fact that we color-coded the cables means that this is like literally match the colors, right? Red is power, positive, black is ground, blue is UPDI, the one single line that's necessary for programming. Now, if you pull out the pinout diagram, you will find that UPDI is basically 4 pins down from ground. So yeah, that's it. Wired. Ready for fuse burning and programming. Before we can actually use the Arduino IDE with one of these, we need to install the megaTinyCore. So just head out to their installation instructions page, and seeing as we're doing the Arduino IDE one, it's basically, well, if you follow these instructions, which I'm going to do, just copy it over, paste it here. If you already have something here, put a comma, then paste it afterwards. Okay, tools, boards manager. Here, just look for megaTiny. Yep. It's this one. Notice there's also the DX core from the same site, and by the way, the microcontrollers covered by the DX core can also be programmed with the UPDI. So that serial UPDI programmer, yeah, it works with that one too. So yeah, reference for the future. Okay, so install. And yeah, that's it. Right, so here you go, tools, and now you have a megaTinyCore under this. So, once you've installed the megaTinyCore in the Arduino IDE with an ATTiny, modern ATTiny part on a breadboard, wired with a serial UPDI programmer, we can now configure it, right? So here from the tools, as usual, and the new group now, megaTinyCore. Well, the first thing you get here, which is different from what you get with the mini core and the AT-megaTinyCore, is that you get groups.
You don't actually get the chip here, you get groups. The second thing is that you choose if you want a bootloader or not here, right? There's not an option saying bootloader, it's here up front. Anything that says with OptiBoot, that means it's with a bootloader, right? Without it, that's without a bootloader. We have a physical part which is an ATTiny 3216, so that's in this group, so that's the one we choose. Now, next thing, now we do choose the chip, right, from that group. One thing, keep this in mind, because it will save you frustration. Always kind of have in your mind, even if you're going to just upload programs, right, that when you wire a new part and you're going to program it, just make sure, check that this is indeed the correct one. Why making sure, right? Well, when you do burn bootloader, when you do upload, the log will be a lot of red text and it will finish in closing COM port. Did it had an error? A lot of red text finishes in closing COM port. Did it went okay? Lots of red text finishes in closing COM port, right? It's hard to tell. You need to actually go there often and scroll up and see, oh yeah, does it look good? And if you've never seen it, it's even worse. And the single biggest cause of that thing not going well, and worse, not going well very early, so it doesn't appear at the bottom of the log, which is what you see after the whole thing scrolls through, right? Is the ID mismatch, meaning the part ID does not match the ID of the thing you chose here, right? That's one of the very earlier forms of failure. So yeah, if you cover it by going like, always kind of having in your mind, yeah, look at this. Oh, this is not ATTiny 3216, it's the 26, so I have to set it properly. And then I do set it properly, right? Saves you some frustration. Now, everything's chosen. Now, I want to point out that there are two kinds of options here in all of this, right? There's the ones that say burn bootloader required. Those things are fuses. The ones that do not say it are not fuses. Now, immediately an interesting thing which none of the classical parts had, and you have it in a modern ATTiny. The clock is not a fuse anymore. The classical stuff, the clock is fuses. Here it's not, it's software. So this configures the Arduino core when you build your program. You don't need, if you change clocks, you don't need to burn fuse, right? It's actually when you build the program that you need to have clocks correctly set here, right? Which clock? Internal oscillator, remember, it's either 20 or 16, several dividers in there, only a few are available here, right? External clock, if you have an external clock generator and you feed it in by the X clock, that's what you care about. The external clock here is for that. And the same thing, all the things that say external clock, really. What does this do? Well, two parts. One part is get the clock from the X clock pin, right? The second part is not really in configuring the clock itself. It's about the Arduino core knowing which dividers to use to get certain frequencies. And for certain timings, for example, millis, right? If you're trying to generate millis from a microcontroller running a certain number of operations per second. So 20 megahertz, that's 20 million operations per second. How do I get millis? Well, I count 20,000 operations. That's the principle of it. SPI, you want to run SPI with 1 megahertz. How much should I divide the core clock in order to get a 1 megahertz core clock? Well, if it's 20 megahertz, I divide it by 20. But if it's only 12, I divide it by 12. So that's why you have to set here the proper one. And remember that the external clock is like a clock signal that's done in the outside, and the microcontroller doesn't really know what it's gonna be. So it's up to you to set this properly to match whatever you're going to feed this part with, right? Now, tuned. To get more precision than the one you get from the factory, you can calibrate your part further. You should calibrate it in the final conditions, right? Already soldered, because soldering a part onto a PCB will alter the error of the internal oscillator. So already soldered. With the voltage it's supposed to be running with, ideally around the temperature it's supposed to be running at, right? Under. And how do you tune it? Well, there are tuning programs, and you get it with the megaTinyCore. There are some tuning programs here under examples. And for example, megaTiny Tuner. There are others. Go and check the megaTinyCore page. From the main page, you will find a page which is all about tuning, and that's what you use for this. Follow the instructions there, run the program in the right conditions, and some values, calibration values, will be stored in a special area of memory. Then when you build your program for that tune part, and that tuning is per physical unit, right? It's per physical chip. A different chip means its own tuning. You can't tune for a series. You tune a chip. And yeah, if that part is tuned, then you can come here and say, okay, I want it to run tuned, and it was been tuned and set up to run with a certain internal frequency. And yeah, you get the options here. Also, this tuning also lets you can abuse the tuning mechanism to run the internal oscillator faster than the maximum supported by the manufacturer for these microcontrollers, which is 20 MHz, and which is why it's here marked as overclock, right? And you can also overclock it by having an external clock, which just so happens to be faster than those 20 MHz, right? Here there's no tuning involved, but again, there's ultimately the result, there's a clock which is faster than 20 MHz. Overclocking means it might not work well. Basically, it's running out of spec, right? Out of the specification for that part. So yeah, it's not guaranteed to work well. It might work well, but it might not. The risk is it might not. The odds are in your favor with this part. For those first few 24, 25, the odds are in your favor, generally, right? You might be unlucky and it doesn't work, but you're likely to be lucky. As you go up, then it starts turning around. And also notice that the kind of errors you can have here, sometimes there are subtle errors, as in the part seems to be working perfectly, and then once in a while, something is actually improperly executed. And those are actually the most pernicious, because you basically have a program that looks absolutely fine and then fails for no apparent reason, right? So beware of overclocking something. It's important stuff, don't overclock it. Let's put it that way, right? But yeah, the options are here, and it's really all up to you. One final note, our programmer runs at 3.3 volts. Because of speed grades, 20 MHz are supported at 3.3 volts. However, for programming, there's the UPDI clock, so it doesn't care if it's 20 or not, because it's the UPDI clock that counts. It's not the core clock. This is all core clock. However, after you finish programming, the part is reset, and then it starts running, and it then tries and sets 20 MHz clock. It might fail at 3.3. 20 MHz, 16, you need to look at speed grades. Basically, 8 MHz would be absolutely fine, for example. It might fail. The odds are in your favor, and I'm going to leave it at 20 MHz because I know the part I have here is absolutely fine with Blink running at 20 MHz, even only with just 3.3. However, it might not run, and don't worry about it, right? You should have designed your circuit for 20 MHz. If you really want 20 MHz, you should have designed your final circuit to provide the appropriate voltage for it, right? So at least 4.2 volts, right? But yeah, if it's just after programming, still wired to a 3.3 volts programmer, and you set it to 20 MHz and it doesn't really work properly, that's okay. That's actually, yeah. You're probably gonna be lucky, but again, you're running out of spec, so you might not be, right? This is also an option, but this is configuring the core. It basically, the implementation in the Arduino core for the millis and micros is going to use what? Normally, the default uses a timer, right? Here it lets you change timers, and you should only do that if you need the default timer for something else, in which case you should know what timers are and how all this works. And beware that other Arduino stuff, and hence Breakstone and Servo, because they are such stuff, other Arduino stuff uses timers, right? So yeah, if you're gonna use the timer that normally gets allocated for things like Tone and Servo, then Tone and Servo are not gonna work because that timer is already busy with millis, right? And there are also other options in this part because of real-time calendar. This one is without the crystal or external oscillator. This will work on a 0 series, this will work on all series, but it will use an internal oscillator, which is really bad, right? So it's not really a real-time calendar with that. It has calendar functions, but it's not really real time. It's really wrong time, basically. But the other two are indeed if you do have an external crystal which is for timekeeping, so of the appropriate frequency, or you have an external oscillator with the appropriate frequency for timekeeping, and those things are quite precise. But notice that's only one, series 1 or series 2, and that at that point you do have indeed a proper real-time calendar. But again, just leave it at default unless you know what you're doing and you need to free up the default timer, right? Startup time, leave it at default. This is just how long it waits before it goes. It's to do with letting things stabilize, right? BOD, same thing as the classical parts, but with more options, right? BOD, you set the voltage, and BOD then constantly checks the power supply of the microcontroller, and if the voltage falls below what's defined here, it goes into reset. Why would you want that? Well, go back to the whole thing about speed grades and about how the frequency of the microcontroller is supported as long as the voltage is at least a certain minimum or above, right? And this kind of dovetails here. If the voltage falls below that minimum, the part is now running out of spec. That means it might fail. Now, in a blink, if it fails, yeah, it's okay, right? You get missed blinks, you get whatever. It's not going to harm anybody. Let's say something is wired to a motor and it fails, and now it's supposed to stop the motor under certain conditions. Otherwise, it might actually damage something. But guess what? It's running out of spec. The program gets random errors. It might actually fail to stop the motor when it should have. And now you've actually got a problem. A genuine, proper problem. So a nasty side effect. Much better if the thing gets there, the voltage falls below the minimum required for guaranteed proper working, right? And the part just stops working altogether. Goes on to reset, everything is switched off for all effects and purposes. At which point your motor is not even going to be activated, rather than being incorrectly activated. That's the point of using BOD. Now, here you have two sets of options. The old days you just said no or you set the voltage. Here you can specify the voltage separately, and then you can activate it, choose to activate or leave it deactivated. And there's also, and this is new, there's more options around activation. So this is BOD constantly on, constantly watching, immediately reacting. This is sampled. Only in this case, once every millisecond it checks it, and then if it knows it's a problem, then it stops, right? And then there's the other one once every 8 milliseconds, right? And there are different variants here. You should check the pages about this in the megaTinyCore website and the datasheet. The purpose of the other samples is to use less battery, right? Sampling, and the slower even sampling, uses less battery. If you're running on battery, it uses less power. If you're running on battery, the battery doesn't deplete as fast. That's why you would want to choose one of these rather than the constantly on BOD, right? If you do need BOD. Let's say for Blink, we don't need BODs. We're not going to use it. Notice this is now burn bootloader required, so this is fuses, right? This EEPROM fuse. When you upload a program, should the EEPROM remain as it is, or should it be automatically erased? Not retain is automatically erased on upload. I'm going to leave it be. UPDI, okay. UPDI is not a reset pin. It's a UPDI pin. It doesn't reset, right? It won't work like that. It's only for programming. But you can, not here, but if you have something like AVR Dude, you can actually change the fuses and transform it into, change its mode. It stops being UPDI and becomes reset. Or it stops being either, it becomes normal IO pin. There's 3 modes for that pin, right? Here, this core doesn't let you do it via the Arduino IDE because you cannot program it anymore if you move it out from being UPDI. You need a special programmer, high voltage programmer, and which is completely different. You can't really make one just like that, and it's not supported by this core. So the core doesn't let you switch off the ability to program your part, right? However, it does let you switch on a reset pin. And that's PB4. PB4 is normally on 2 series only, as you see here. PB4 normally is an IO pin. It's an absolutely normal IO pin. However, via fuses, it can be configured to become a reset pin. So if you do activate this, then you will have in that part, and remember this is fuses, you will have a UPDI pin and then a different pin, which is indeed a reset pin. That's the purpose of this. Now, our chip there is a 3216, so it's a 1 series part, so it doesn't even have this, so we're not going to do anything here. Printf, this stuff is now again, notice no burn bootloader required. This is about configuring your Arduino core again when you build your program. It's not about burning fuses, it's about building your program. This is about the function that exists, really old C function that creates text string out of a text constant with some formatting and values that are stored in variables. That's what printf does. And well, the various variables can have various types, including floats. And there's various configurations about the formatting in which the numbers are going to be displayed and other things, not just numbers. So yeah, printf can be a little on the big side. And it's even worse if it actually supports floats, because there are multiple ways of displaying floats and many more options for them. And you see here it actually adds 1.2 kilobytes of code using flash memory, so code, if you want to add float support for printf. And this is all about this. Why does this exist even? Well, remember, some of the parts here are 4 kilobytes or even 2 kilobytes. So at that point, it starts getting really, really important that, you know, I need printf, but I don't need to use it to float. So let's not bring in the whole code that does floats, because it wouldn't fit anymore my program. That's the whole point. Now, if you don't use printf, leave it at default, because it just does the normal build process, which if you don't use something, it doesn't get brought into your program, so it doesn't use any memory at all, right? If you do use printf, then yeah, do you need it with floats? Do you need to print float to create text strings using values stored in floats, or can you do it without it, right? That's basically it. Notice that if you choose anything other than default and you do not use printf, the code is still going to be brought into your program, because it doesn't use the normal build process, right? Even if you don't use printf, printf code will be there, and you probably don't want that. So if you don't use it, leave it at default. If you do use it, don't care about floats, leave it at default. If you do use it and care about floats, then do the full, right? I'm going to leave it be. Wire, it's a similar kind of purpose, but it's a different thing. This is about wire being capable of supporting being part of the time a master and part of the time a slave. In the same program, the program can at times be master and at times be slave. This is incredibly unusual, right? I cannot really think of a situation where it makes sense. But yeah, sometimes it might, I guess. So the option is here to have that, but if you don't need that, which is 99.999% of the time, leave it on the default, which is always a master or always a slave, right? And that uses less flash and even less RAM. I'm going to leave it be. Watchdog timer, these two. Okay. Main thing, don't activate this unless you know what this is, because it will make your program not run. Watchdog timer is a means of the hardware detecting that the program is out of control. There's some bug, memory overrun, whatever. It's out of control, so it forces the reset of the microcontroller. That's what this does. However, your program has to do things to tell it, I'm fine, I'm working fine. So your program has to support certain things. It has to be there in the code. If you've done a normal program with nothing about watchdog timer and you activate this, you know what happens? The program resets. And after whatever time you put here, really, the thing starts running and resets. And then, yeah, you're wondering why is this thing not running properly, right? Yeah, this would be why. So don't use watchdog timer if you don't know what you're doing, right? Go check go read about it, even. Go check the megaTinyCore pages, go check the datasheet before you actually dive into this. And notice that here is burn bootloader. This sets it in fuses. So you can actually activate the watchdog timer functionality on your software. You don't need to set it in fuses. If you set it in fuses, you force it to always be on. That's what fuses do. So it's even worse than just, if you're trying it out, if you want to try it out in your software, add the codes to activate the watchdog timer in software. It's going to be all of this is going to be explained what to use in the megaTinyCore page for it. Again, from the main page, it's going to be a link for that. read that, do that, try it first from the software if you want to. And yeah, only activate this when you really know what you're doing, because this forces watchdog timer on, which would mean a program that doesn't support it properly gonna reset. It's just not gonna work, and you're gonna be wondering why is it working, right? Okay, so I'm gonna leave it off. This is the COM port of your serial UPDI programmer. So yeah, and this is the actual things about the programmer. So let's first kind of exclude the stuff we don't care. These are boards which have built-in programmers, we don't care, right? These are professional programmers. For this video, we don't care. If you have one, yeah, use it, right? But here we're not really going to touch it. This is the old way of doing this, right? It's called JTAG to UPDI, and you could also make a programmer for this, but this is not how it's done anymore, so we're not going to be looking at this now. That leaves us all serial UPDI stuff. This one, this is, if nothing else works, try this. Really, that's the point of this, right? It shouldn't be needed, but yeah, maybe you put it here and it works, or you put it here, it doesn't work, in which case you do have problems, right? This is the last ditch effort to get it to actually do something. The other ones come in pairs, and each pair is about a different UPDI clock. This is the clock for 4 MHz. This one is the 8 MHz, and this one is the 16 MHz, right? Why all this? Why not just the fastest? Well, because also the voltage of your programmer means that only clocks of a certain speed can be used. With the 3.3 programmer we have here, we could actually quite possibly get away with using one of these, because it's only 8 MHz still supported at 3.3, but certainly the 4 MHz, yeah, fine. And the default one is actually the best one for this programmer, right? Why 2 of each? Well, it's to do with the different chips that might be present in the USB to serial adapter, which you use to make your serial UPDI programmer. And different chips have some different flags and some different things that have to be done. And you can see here more clearly that, for example, the CH340 family, you should try this. And actually the programmer we have uses one of those chips. You should try this one. It's probably this one's going to work. But if you have an FPDI, maybe it's the other one that's going to work, right? So try one. If it doesn't work, try the other one. That's basically the principle. Also, sometimes different operating systems might have different things. Notice for the fastest, even if you are feeding in the 5 volts, in the appropriate voltage, whatever, it might still not work because the USB to serial adapter that you have is not actually capable of running that high baud. This is almost a million baud, right? So it's not the microcontroller anymore that might be the problem. It actually might be somewhere else. It might even be in the drivers for Windows, right? So yeah, for us, we just use the 3.3 volts thing we have, and it's default and it's fine. And frankly, for this part, you're not really going to notice the difference because, yeah, this is seconds anyways, right? So there you go. Now, yeah, let's burn any fuses we might have done. Notice here the detail I mentioned before about red text closing COM port. Is this okay? Is this not okay? Well, if I go up and I scroll, I can start seeing, yeah, okay, writing for bytes. I know it's 1 byte per fuse, so yeah, that looks okay, right? But yeah, this can be a bit deceiving, and as I said, getting the part wrong here is the most common kind of problem. So it's a good idea to just keep it in your mind. Yeah, just make sure. Yeah, I wire a part and then I'm going to program it. And before I do it, I just come here and check it. Yeah, it's okay, right? And yeah, upload. It's normal upload. Now, one surprise here. LED built-in. This is not pin 13, right? If you've wired it to pin 13, expecting it as normal that it's going to be there, and you have your LED there with the resistor, and it's not going to blink, right? Everything went fine, it's just not blinking. It's not there. In this core, LED built-in is pin 3, right? And because this core has to target parts with also 8 pins, which don't have 13 Arduino pins, and also 14 pins, which also don't have 13 Arduino pins, because of those 14 pins, one is power, one is ground, one is UPDI, so there's not enough pins for that. So only the 20 pin parts really have 13 more than, obviously, but have a pin 13 in Arduino, right? So yeah, for all things, it's going to be pin 3, Arduino pin 3, not a physical one, so check it out in the pinout diagram, and yeah, wire it there, and yeah, it will work fine.